subspace polynomials, and this is joint work with Eli Ben-Sasson. So I'll quickly define what this object affine dispersers are, and then I'll tell you very quickly, and it's a very simple clean object, and after that I'll tell you what the plan for the rest of the talk is. So at least an affine disperser, as in this talk, is it's a function, it's a 2 coloring of f2 to the n, such that every d-dimensional affine subspace is not monochromatic. Okay, so it's so let me just say that. So an n-d affine disperser is a function f from f2 to the n to f2, such that for all d-dimensional affine spaces, f of a is non-constant. So I mean it's all of f2. Okay, so and the thing that I want to talk about in this talk is how to construct explicit affine dispersers. So the fact that starts everything is that a random function f from f2 to the n to f2 is a n order log n affine disperser. Okay, and the whole goal is to try to give explicit functions f that have the same property. So fact random f is n log n with high probability. Okay, and how do we construct explicit functions f that have the same affine dispersion property? Okay, and so I won't do an n log n affine disperser today, but okay, good. So the plan for the talk is so first I'll talk about the motivation for studying affine dispersers. So it comes from randomness extraction, and so I'll tell you some things about affine dispersers and affine extractors and what was known prior to this.
Is the font big enough? Should they write bigger? No, it's good.
Okay, and then I'll introduce the tools that we'll use for analyzing some affine disperser constructions. So I'll actually give you the statement of, I'll give you explicitly what the affine disperser is. So it's a very easily describable function, and then but the tools for the analysis of it will start requiring some work. So then I'll introduce these things called subspace polynomials, and we'll prove some fun properties of them. And then finally we'll use the subspace polynomials to analyze the affine disperser. So right, so okay, so let me state the property of being an affine disperser in a slightly different way. So suppose x is a random variable that's uniformly distributed over a d-dimensional affine subspace of f2 to the n. So uniformly.
Maybe you should write bigger.
Okay. Okay, then f is an affine disperser if it's true that for every such x, f of x is non-constant. So we took something which I'll call which you should think of as a weak source of structured randomness, a weak structured source of randomness, and we produce something that's so it's one bit which has a little bit of randomness in it. Okay, so you produced a non-constant bit. So an affine extractor is something where you can guarantee that f of x is in fact a uniform bit. Okay, and more generally you can ask that f doesn't just map from f2 to the n to f2, but it maps from f2 to the n to f2 to the m, and and f is uniformly distributed over its range. So, right, so an affine extractor is so it's an f such that for all such x, f of x is nearly uniform. Okay, and so in the sense it takes a structured source of randomness that's sort of weak and it purifies it into getting purely uniform bits out of this thing. And and this is exactly the context in which these objects arose. Okay, so and what I want to do is construct these objects and right. Okay, good. So okay, so it's an easy fact that so the first affine dispersers come from the following simple observation that so if you have a function f such that all its Fourier coefficients are bounded by 2 to the minus delta n, then it is an affine disperser and even an affine extractor for subspaces of dimension 1 minus delta times n. Okay, so if f is such that so if you look at the function minus 1 to the f, which is now a plus minus 1 real valued function, and all the Fourier coefficients of it are less than 2 to the minus delta n for xi non-zero, then this implies that f is a n 1 minus delta times n affine disperser extractor.
For extractor, you have to subtract a little more and you get it in the error.
Oh, right. Oh, good. So then it's a 1 minus delta plus epsilon affine. Okay, so that means precisely. Okay, and so since this is a Boolean function, we know that it will always have some Fourier coefficient that's larger than 2 to the minus n over 2, and so this general recipe for producing affine dispersers will not produce an affine disperser whose which is n anything less than n over 2. Okay, so if you want to disperse from affine subspaces that have dimensions strictly less than n over 2, then one has to do something which doesn't just look at the magnitudes of Fourier coefficients, one has to analyze it somehow differently. Okay, so the first affine dispersers that started going below n over 2 were given in 2005 after the sum product revolution. So Barak-Kindler-Shaltiel-Sudakov-Wigderson in 05 gave explicit n delta n affine dispersers for any constant delta greater than 0. Okay, and the tools that were used for this construction came from the sum product theorem, which so I won't exactly state precisely, or I won't even state, but some cousins of this sum product phenomena will show up later on in our talk. Okay, and then Bourgain subsequently was able to give explicit n delta n affine extractors for any delta greater than 0. And in fact, so I'll be a bit more precise. So explicit n over root log n affine extractors, and in fact these extractors so they didn't just output one bit, they could output a linear number of bits or these many bits, and the error in them was also exponentially small. So meaning, and here the error I mean the proximity to uniform of the output of this extractor. So these were really strong objects, and they seem to be they started tailing off once you started going slightly below sublinear dimension. So, and recently Amir Yehudeh simplified the analysis here and removed one of the logs in the analysis. So, I mean, I guess now, and they're still affine extractors. So, it's n over root log n. Okay, and so the analysis of these two also used heavily the sum product theorems in the form of exponential sums, which were proved by Bourgain, Glubachuk, and Konyagin. So, okay, so the main result that I want to talk about is an explicit. An explicit n to the 1 minus epsilon affine disperser for a certain positive epsilon greater than 0. So, there exists n to the 4/5 affine dispersers. And okay, and so let me just tell you what this explicit n to the 4/5 affine disperser is, and then the rest of the talk will just be the analysis of this disperser, and we'll see lots of things along the way. So, okay, good. So, so I have f2 to the n, and I'm going to view it as f2 to the m whole to the s for some choice of m and s. Okay, so I mean, so just for reference, m and s are both of the form n to the constant. So, okay, then so any input x in f2 to the n. So if I'm defining this function f from f2 to the n to f2, I can treat it as an s tuple of elements from f2 to the m. So, I look at them x1 up to xs, okay, and I am going to plug these xi's into some polynomial and output the value. Okay. So, and let me just tell you what that polynomial is. Okay, good. So, I will first look at x1 cube, x2 to the 7, x3 to the 15, etc. up to xs to the 2 to the s plus 1 minus 1. Okay, and so I'll take all these numbers and plug it into an elementary symmetric polynomial, the tth elementary symmetric polynomial. So, this is the sum of products of t of these at a time. Okay, so far this calculation has outputted something in f2 to the m. Okay, and then I want to output something in f2, and so then I'll take the finite field trace from f2 to the m to f2 of this. Okay, so let me just clarify what I'm saying here. So, trace of z is z plus z square, etc. up to z to the 2 plus z to the 2 to the 2 plus, etc. up to z to the 2 to the m minus 1, and the symmetric polynomial of y1 up to ys is the sum over all of overall t tuples, products of t tuples. So, I contained in S size I equal to t of product of I and I of yi. Okay, and this is the function. So, so the one last qualifier that I want to give is that and when you choose the m and the s such that f2 to the n is equal to f2 to the m whole to the s, you want m to be prime. Okay, and this is a strange condition, and I will explain why such a condition is necessary. But right, so this is the whole construction. The claim is that this is an n to the 4/5 affine disperser.
And it may be an extractor.
It may be an extractor for all we know. In fact, it's highly likely to be an extractor. Right. Okay. Okay. So right. So now I'll completely stop from this. I'll start. I'll define these things called subspace polynomials, which will help analyze this thing. And so after a good detour into subspace polynomials, and we'll pick up a few facts about them. Then we'll come back and try to analyze this. Yeah. Oh right. Oh good. So there's another world where people study affine dispersers and affine extractors over fields that are not F2. Okay, so over larger fields. Okay, so briefly let me summarize what the results are. So one very striking result is that okay, so again, so I want a function f from fq to the n to fq to the m that outputs some number of bits, and for all d-dimensional affine spaces so A, then if you take x which is uniformly distributed over A, then f of x is near uniform. Okay, and this is the definition of affine extractor over fq. And so when q is large enough, in fact when d is equal to 1, you can have affine extractors. So you don't even need log n dimensional spaces to start extracting uniform bits. You can even do it with one dimensional spaces.
So basically in both cases you need about n points in your subspace.
Right. Oh right, good. So yeah, so when q grows bigger, one dimensional spaces already have a lot of points in them. So that's where we get saved. So Gabizon and Raz showed that. So they gave explicit constructions of these things. So they said that when q is greater than n to the c for some constant c, there exist explicit affine explicit affine extractors that have that are as good as you can hope to have. And more recently, Gabizon and DeVos, just very recently, gave an intermediate result that allowed you to reduce the field size q and simultaneous and with a trade-off in increasing the dimension d. So they gave a graceful trade-off of this result. So this earlier result only worked when q was bigger than n to the c for some fixed positive constant. C was something like 20, and if you want a graceful trade-off between q and the dimension d, then Gabizon and DeVos gave this construction. So and the tools that appear in these works are they're related to the Weyl bounds for exponential sums. And similarly, so q d trade-offs.
Is q bigger than n over d? Polynomial n over d.
So that is the trade-off here.
Q bigger than some power of n over d.
So q bigger than n over d to the c. Okay, that sounds okay. Right. So for delta in dimensional spaces, you need q being just 1 over delta to the constant. Right. Okay. So right. So that's the story over small fields. This is the story over big fields. Nothing we say really. Improve. So there's very little to improve over big fields, and nothing we say has anything to do with it. Okay, good. So let me start with subspace polynomials now. Are there any questions so far? Everybody's fine. Okay.
If you want, there are lots of white charts in the. If you want.
Oh, I'm fine. For
is this color chalk matter, though white is better?
perfect. Okay, great.
So do you really depend on theorem? If you're best with F3, will the technique still give something?
Oh, so then it's so usually when you define affine disperser, you would have defined it as the image of f is all of f3, but the techniques that we use will only give you f is non-constant.
But it will give a non-constant polynomial.
It will give a non-constant polynomial over f3 also. Right.
It's not of constant degree. This.
So no, the degree of this. So these are all of degree n to the constant. So yeah, some polynomial in it. Okay, so good. So I'll first define what a linearized polynomial is. It's a univariate polynomial over f2 to the n that has the only exponents that appear in it are powers of 2. So it's a polynomial of the form summation ai x to the 2 to the I. Okay, so one fact that I want to say is that okay, so first it's clear that so linearized polynomial gives you a map from f2 to the n to f2 to the so are we working over f2 to the m? Okay, so over f2 to the m. So any such linearized polynomial gives you a map from f2 to the m to f2 to the m just by evaluation, and the claim is p is a linear function. Okay, so p of x plus y is p of x plus p of y. Okay, and so why is that? Because if you plug in x plus y into x to the 2 to the I, then you get x to the little x to the 2 to the I plus little y to the 2 to the I, because raising to the power 2 is linear over characteristic 2. Okay, so so I also want to say that every linear function from f2 to the m to f2 to the m can be written as in the form p of x for some linearized polynomial p. Okay, so why is that? Well, it's going to be by counting. So the total number of free bits that are available in linearized polynomials are m. So each ai comes from f2 to the m, and there are m of them. So that's 2 to the m square different linearized polynomials, and the total number of linear maps from f2 to the m to f2 to the m is also 2 to the m square. It's the number of entries you can fill into an m by m matrix. So the total number of so the fact that we want to record is linearized polynomials are in one-to-one correspondence with linear maps. So and so by linear I mean f2 linear, just to be okay. So amongst the space of all these linearized polynomials, there are some special ones which are called subspace polynomials. So and there are two kinds of them. So the first one is it's going to be so given a subspace A, its kernel subspace polynomial is the lowest degree polynomial, the lowest degree linearized polynomial that vanishes on A. Okay, so and it so turns out that it's also the lowest degree polynomial that vanishes on A. So if A is a linear subspace, of f2 to the m, and it's an f2 linear subspace, then if you define pa of x to be product over all alphas in A of x minus alpha, then the claim is pa of x is linearized. So this is the smallest degree polynomial that vanishes on A. When you do this multiplication out, the claim is that you will get a linearized polynomial. Okay, so let me try to show this quickly. So first I'll
So linear map, or is the function that, you don't say what it gives on other points.
Right. So this only says it vanishes on A. It could be do arbitrary things on outside, but in fact it's going to be linear even outside. Okay. So
It will be constant on cosets of A.
it's going to be constant on cosets of A. Yeah. Oh, is that the proof already? Right. Oh, good one. Yeah.
So then,
So
as if you shift all the alphas by the same.
so does that mean it's linear yet? Or?
No, it doesn't mean it's linear, but at least it's constant.
But it's constant on cosets of A. Right.
Then probably, but probably you can see that different shifts.
Right.
That I don't see.
Oh, okay. Right. Okay. So it's so one can prove it in many ways. So you can certainly prove it by induction on the dimension of A, just by building up A one by one. But so let me just show it in another way. So if A is dimension D, so I want to say that there is a polynomial summation ai x to the 2 to the I going from 0 to D that vanishes on A. Okay. So why is this? Well, if I make such a polynomial vanish on just a basis for A, then it will automatically vanish on all of A, because such a polynomial is always linear. Okay. And how many elements form a basis of A? Well, they are just D elements that form a basis of A. So some linear combination of these D plus 1 functions is going to vanish entirely on that. So therefore, there is some polynomial of the form summation ai x to the 2 to the I going from 0 to D that vanishes on A. And at this point, it's clear that this polynomial has to equal that polynomial, because here is a polynomial of degree 2 to the D that vanishes on a set A which is of size 2 to the D. So it has to be this, okay, or a scalar multiple of this. So therefore, this is linearized by an indirect method. Okay. So all right. So that proved that P of A of x is linearized. So for every linear space A, there is a polynomial that vanishes on A, and in fact this polynomial is linearized and it's of degree exactly 2 to the D. Okay. So these were what I call, so P of x, I mean, so is called the kernel subspace polynomial. So before this, there only used to be subspace polynomials, but so we call this kernel subspace polynomial because there's going to be a different kind of polynomial, subspace polynomial, coming up soon. Okay. So the next thing I want to define is the image subspace polynomial. So the image subspace polynomial is going to be a polynomial whose image when you evaluate on all points of f2 to the m is equal to the set A. Okay, and its degree is going to be the lowest possible degree you could hope for, given this given the size of A. Okay, so
Is in particular an image, subspace polynomial of the
exactly right. So P of x, right, right, and dual is sort of something, right, exactly. So P of x is a polynomial of degree 2 to the D. It has a kernel of dimension D. Therefore, it has an image of dimension n minus D. So I have a polynomial of degree 2 to the D whose image consists of 2 to the n minus D points. So if you think about it, this is the lowest possible degree that you could hope for any polynomial to have an image of size 2 to the n minus D. So so if A is, so this is actually a claim because it's not. There is a polynomial qa of x such that qa of f2 to the m is equal to A. Okay, and degree of qa is equal to 2 to the m minus d. Okay, so a degree, I mean a polynomial of degree 2 to the m minus d can be at most 2 to the m minus d to 1. So, if it is going to map all of f 2 to the m into a set of size, so the smallest set that it could map it into is a set of size 2 to the d. Okay. And so, one example of a polynomial that has this nice property is a kernel subspace polynomial, because we just looked at its degree and we noticed that it is, I mean kernel subspace polynomials are definitely polynomials of this kind, meaning their image is equal to some affine space A, and its degree is as low as it could be for having that image. So, but now the claim is that for every affine space A, there is indeed such a polynomial whose image is equal to that. Okay, so let me prove that too. So this is a really clever trick, and so it shows up in the book of Berlekamp on algebraic coding theory, but it's really clever. So okay, good. So I started with A, right, and I want to find a polynomial whose image is equal to A. So I mean, maybe I should drop it. So this is A, and this is all of f 2 to the m, and somehow I want a polynomial that maps it like this, and it should be of as low degree as possible. Okay, so what we will do is we will look at the polynomial PA. PA is a polynomial that vanishes on A. Okay, so it is not at all what we want. Okay, and we will look at the image of PA. Okay, so this map is PA. So PA sends A to 0, but it sends everything else to something of so the image of PA. So I will define B to equal PA of all of f 2 to the m. Okay, and the claim is, if you look at PB, its image is A. Okay, so in words, the image, so the polynomial QA is the kernel subspace polynomial of the image of the kernel subspace polynomial of A. Okay, and right, I mean there is no reason to suspect that at all in the beginning, but okay, and the proof is really neat. Okay, good. So so I took B to be PA of f 2 to the m, and I want to say that PB has image A. So it would be enough. So first, I mean, it's easy to check that the degree of PB is precisely 2 to the m minus d, right? Because yeah, was it okay? So because well, the dimension of B is m minus d, because it's PA is a linear map of kernel dimension d. Now, what do I know about PB? Well, PB vanishes on the image of PA, because that is the definition of B. So, PB of PA of x, I mean, always evaluates to 0. Okay? And so, the degree of this was 2 to the d, and the degree of this was 2 to the m minus d, and if this always evaluates to 0 for every x in f 2 to the m, what that means is this must equal x to the 2 to the m minus x is the claim. So, here this composition is a non-zero polynomial of degree 2 to the m, and it vanishes on every element of f 2 to the m, and there is a unique polynomial that vanishes on all of f 2 to the m up to scalars. So, I mean, but that will not affect this. So, PB of PA of x is equal to x to the 2 to the m minus x. Okay. So far we have got that. But what do I want to show? So, want that the image of PB is contained in A. So, I want to show that PA of PB of x is I mean, so this evaluates to 0 on every element of f 2 to the m. So, I want to show that PA of PB of x is equal to x to the 2 to the m minus x, right. this is precisely what we want to show, because the degrees are again 2 to the m minus d and 2 to the d. So, and if I want to show that it vanishes on every element of f 2 to the m, then this is what I need to show. Okay. So, I am going to go to this equation and put a PA on the outside, that is equal to PA of this. Okay. But now I can do something. So, PA is a linearized polynomial. So, PA of x to the 2 to the m minus x is equal to PA of x to the 2 to the m minus PA of x, and PA is also a polynomial with coefficients in f 2 to the m. So, PA of x to the 2 to the m is PA of x whole to the 2 to the m minus PA of x. Okay. So, now let us look back at what we showed. We showed that PA of PB of something, and that something is PA of x, is equal to something to the 2 to the m minus something. So, I mean, so this means that PA of PB of y, a formal variable, is equal to y to the 2 to the m minus y. So, that is exactly what we wanted to show. Okay. So, you will certainly admit that this is a really clever trick, at least. Okay. So, this shows that right. So, for any affine space A, there is a polynomial of as low a degree as you could hope for, that whose image is equal to that space A.
You get it just by considering the actual linear maps that zero out the kernel and that give the image, and the linear maps themselves, the F2 linear maps, are in one-to-one correspondence with the polynomials.
Right.
If you have the linear map that that it precisely is 0 on A.
But there are many such. There are many such linear maps. We are also considering the f 2 to the m degree, which somehow mixes strangely with this.
Well, every linear map is in one-to-one correspondence with the polynomial.
Right. And or every linear map, but so there are many linear maps that vanish on A. When we work over just f2, it's hard to distinguish which one is PA, because PA is also characterized by a degree condition on.
Use the counting. I mean, count the number of maps with image A. Just by counting, one of them will have low degree.
Yeah, but we don't know. I mean, before this, I don't think it's easy to see that two subspace polynomials of the same degree could have the same image for all we know. There's nothing to rule that out, as far as I see. Yeah.
How do you get the conclusion that from PA, PB, PA of x equals PA of x to the 2m? How do you get that?
Oh, so I mean, I'll treat PA of PB. So I can, okay. Let me call PA of PB of y minus y to the 2 to the m minus y. I'll call that polynomial G.
Right.
And G is a polynomial such that when you plug in PA of x, you get 0.
Right.
So this, but I know that if G is a non-zero polynomial, and if you plug in any positive degree polynomial into it, it will have positive degree by just looking at the highest degree term. So if I have a polynomial G and I am plugging in some polynomial h of x into it, and G of h of x is 0, I mean, so the degree of G of h of x is the product of the degrees, and so that means. Okay, so so far we have this. Okay, great. So and this is really so the image subspace polynomials are really what we'll need for doing the analysis. So let me start doing the analysis. Oh yeah.
Can you explain this again? Because it seems for a moment that you're proving this relation for PA of x, which is y. You're changing the PA of x by y.
Right.
But this y is a guy that belongs to the subspace B. Right, because PA of x lives in B.
No. So this is an equality of formal polynomials. I'm not saying I'm not thinking of x as a substituted element of f2 to the m. Yeah. Okay. So then this is P of x, the polynomial, and so this is and so is that okay? So it's not. I'm not doing substitutions.
Okay.
Yeah.
So I guess
Okay. Okay, good. So what?
You should have written that what you want is the
Oh, right.
Then it would be.
Oh, right.
Then you would just equate y.
Right. And this is equality of formal polynomials. Yeah. Okay. So image subspace polynomials parameterize a subspace, right? I mean, it's something whose image is equal to this, and so when we show that something is an affine disperser, we'll take the subspace on which you want to show some polynomial is non-constant. We'll first parameterize it in some way, and then just open things up. Okay, so let me start looking at the function. So I'll try not to erase this. Okay, so I have this. So now A was a linear subspace of f2 to the m, but A is now going to be a linear subspace of f2 to the m n, which is f2 to the m to the s from now on. So okay, so then okay, so the first step of the analysis will take that. So we're interested in f of A, right, where f is that particular function, and so the first step of the analysis is going to do it's first going to parameterize A using these image subspace polynomials in some way, and then there's going to be some reductions, and it will finally reduce to a statement of the following kind. And this kind of statement also appears in the analysis of Bourgain and Yehodeyev. And so I'll state that statement. It's the intermediate target statement that we're aiming for. It's a very clean statement, and okay, so just because we are going to be proving affine disperser and not an extractor, it's going to be a little bit easier in our setting. And once you reach this setting, the Bourgain approach would have gone one way, and we'll go completely differently. So, okay, so this sort of sub theorem, and later on I'll change the statement of this theorem slightly to ask for something more. So, so we're working over f2 to the m, a1 etc. till at are subspaces in f2 to the m. Okay, dimension of ai I'll call di, and then ei's are going to be some integers, and I'll let alpha I be equal to 1 plus 2 plus 4 etc. up till 2 to the ei. Okay, so the setup looks formidable, but it's going to be really simple. So okay, so then I'll define the function g of y1 etc. up till yt to be the following: trace of product yi to the alpha I going from 1 to t. Okay, and so g is a map from f2 to the m to the t to f2. Okay, and then the claim. Oh, right. And and I'm going to assume that there's a lot of dimension sitting inside this. So summation di minus ei plus 1. So ei's are to be thought of as small. So you for the moment one can even take ei to be 1 in this theorem. So just to get a feel for it. Sum over all I going from 1 to t. If this is greater than m, so these are all hypotheses so far, and and I'll add one more hypothesis, that ai is not contained in b times f2 to the r plus c for r less than m. So none of the AIs are contained in an affine shift of a strict subfield. Okay, so the AIs are completely they are not very so for instance, if you assume M is prime, there are no subfields whatsoever, then AI will not have this property. So given all these assumptions, then the conclusion is right for any r strictly less than M and dividing M, otherwise that subfield won't even appear, so that's not an issue, right. So and so given all this, then this implies that G is non-constant on A1 up to AT. Okay, so G of A1 AT non-constant. Okay, so this is for independent samples, right. So if you get
You plug all, it just, you evaluate on all points in this Cartesian product.
right. So on the Cartesian product, I want to say this is non-constant. So this is qualitatively an easier looking statement than the statement of that earlier affine disperser. So the earlier affine disperser, I had a single affine space, and I said that if I take a random sample from it and plug it into this function f, then it's non-constant. Here I am getting independent samples, one from each AI, plugging it into this just this monomial product yi to the alpha I for certain alpha I. So if all the EIs were equal to 1, for instance, which is a pretty decent case to think about.
1 or 0?
So EIs actually had to be all right. So EIs also had to be greater than 1 for a silly reason. Sorry, or greater than or equal to 1. So so if I think of EI as 1, then all the alpha I's are equal to 3. So I am taking the product of all the yi cubes and taking trace of that, and the claim is that this function is non-constant as long as the sum of the dimensions of the AIs is large enough. So sum of the dimensions is greater than M.
You have to let AIs be affine.
You have to let AIs be. Oh no. So this does not hold when AIs are. Sorry. Let me rephrase. I don't know how to show this when AIs are not affine subspaces, but Bourgain does. So the approach coming from the sum product direction will actually show that things like this are non-constant under suitable hypothesis. So there may be something else, but so this theorem that which I will show here will require them to be subspaces.
Do you know anything about the distribution before you take the trace?
No. So
This monomial,
the distribution of the monomial before taking the trace.
the value of this monomial before you take
No. So yeah, essentially, so nothing other than the non-constants and some very tiny thing will. So the analysis of Bourgain, etc., also reduced to this kind of theorem, and but there was always an assumption of the form di has to be a constant fraction of M or nearly a constant fraction of M. So the place where things are getting, so the place where I mean one can start going sublinear in sublinear dimension is that this theorem does not require the di's to be, there does not require any lower bound on the di's. This just holds for I mean every set of di's, as long as this happens. Okay, so
And this reduction will work for up to some relation between M and S.
this
Reduction to this statement.
the reduction to this statement, so if you are just asking for an affine disperser, then this reduction will essentially work for everything. For just an affine disperser, this kind of
But then you could have taken S to be, I mean, the reduction will work because here there is no T is S, so it is like.
a T will be related to S.
Okay, so
Yeah.
Okay, good.
Oh yeah.
What about the EIs? I mean, why not just take the EIs to be 1?
Oh no, so the reduction from that so that symmetric polynomial has a whole bunch of monomials. Each monomial will have yi to different powers alpha I. So in order to handle all those monomials, so I mean it's needed because of the choice of that function. So here one could take all the EIs to be 1, and
Large EIs is to get independence.
the choice of large EIs is to get independence, right? yeah, in a sense. So, this is a disperser. So, I mean it is the disperser analog of independence, but we will see why. Okay, so right, so the best, I mean if you want to plug in parameters in this just to get the best independent source affine disperser, then you would plug in Ei is equal to 1, but just for that theorem you need to do it with different Eis. Okay, so the first half is going to take that polynomial and start reducing to a statement of this kind, and I will actually strengthen the conclusion here slightly later on, but when we need it. Okay, so good. So the goal is now to parameterize this affine space A, which is just a subspace in F2 to the m to the s, and it's of say dimension d, and then we'll study. Oh, good. So we'll have some map H from F2 to the m to the s to F2 to the m to the s, such that H of A. Sorry, the image of H is all of A. Okay, so we want such a map first, and H, and hopefully H given by explicit polynomials. Once we have such a H whose image is equal to A, then it suffices to show that F composed with H. So then it suffices. That F composed with H, when you look at its valuations on all of F2 to the m, is non-constant. Right, because we just parameterize the set A.
The same would be with extractor. If you were aiming at proving that it's an extractor, all you would have to do is that this composition is an extractor.
Right, right. So then we would try to show that F composed with H is unbiased, and that would show that F is an extractor if you could show this for every affine space A. Yeah. So at this point we haven't lost anything. Okay, so let's construct this map H. Okay. So it's just so A was not a linear subspace inside F2 to the m. If it was inside just a single field, then the image subspace polynomial was the answer. Now it's just going to be a slight variation of that. So it's okay, and so the following fact was was also used by Bourgain. It says the following. So I mean, oh, I see. So already in BKSSW. Okay, so so the same construction comes from BKSSW also, and we're saying, okay, so let A be your affine space contained in F2 to the m to the s. Then there exists affine spaces A1 etc. up to AS contained in F2 to the m, and linear maps sigma ij mapping from AJ to F2 to the m such that, okay, well, one, this okay, so the most crucial one, A is exactly equal to the following. Well, so A is
say verbally that you are going to diagonalize this subspace, right? That's
oh,
the basic.
right, right. Oh, good. So we're going to take the basis for A written. So the row, I'll take a matrix where the rows are the form a basis for A, and I'm going to sort of put in echelon form, and okay, and it will lead to the following decomposition. So once I state the decomposition and I said echelon form, it should be sort of clear that what happened just now. So it's exactly equal to the set of all B1 etc. up to Bs, such that there exists A1 up to As in product Ai with Bi equal to Ai plus sum over all j less than I of sigma ij of aj. Okay, so B1 is, so I'm going to write every element of A in the following fashion. First I pick an arbitrary A1 up to AS inside product AI, then I set B1 equal to A1, B2 equal to A2 plus some linear function of A1, B3 is equal to A3 plus some linear function of A1 plus some linear function of A2, etc. Okay, so and so that's exactly what I wrote here. So every linear space, every affine space A, I have parameterized in terms of these spaces AI. Okay, and the second fact is that the sum of the dimensions of AI is equal to the dimension of A. Okay, so the dimension of AI is precisely the amount of entropy in AI conditioned on the first I minus 1 blocks. Okay, so I hope this is intuitive enough that. So I wasn't planning on elaborating on this, but this is the decomposition that holds for any affine space A, and it should hopefully it's pretty intuitive.
If you draw just a vector, or if you draw the vector, if you draw a vector, some element in A which is just an S star, so there is the entropy to the first coordinate. That's what you'll have in the first coordinate. That's what A1 will be. You condition on this and proceed.
Right, right, and that was the proof. Right.
And that's a linear condition because of linear sum.
Oh, right, right.
And this decomposition is due to.
So it first showed up in BKSSW, and then, but it's it's the echelon form.
We don't.
Most even things which are very
No,
natural.
it's not the reference issue. It's just nobody knows how to do anything without independent sources. So even the affine sources, I mean, for this setting, the affine sources are very structured, but we don't know how to deal with them if we have just one sample. And the only way we can deal with anything is just reduce it to many samples, many independent samples, or almost in. I mean, these are not independent yet. But something like independent then appeal to sample. That's the only thing we know.
Right. So this finds this tries to make them as independent as possible. I mean, it isolates the new entropy in every block condition on the previous so far.
It's almost forced on you if you are going to use some tool. You can do nothing else with it.
Okay, so given this, and and image subspace polynomials, I'll now parameterize it. Okay, so H is the map from F2 to the M to the S to F2. So I'll call H to be H1 up to HS, and HI maps from F2 to the M to the S to F2 to the M. Okay, so good, and I'll define HI of x1 up to xs to be, well, I'm going to try to fake this calculation inside the HIs. So it's QAI, so this is HI, this is QAI of xi plus sum overall j less than I of some map of the form Pij of xj, where this is linearized and this is the image subspace polynomial of AI. Okay. And the claim is you can always find linearized polynomials Pij such that okay, so right, such that when you look at this tuple h equal to h1 up to hs, then the image of h is precisely A. Okay. So, why is that? Because the image of QAI is always going to give you an element of QAI, the image of QAI is going to be this element little ai, and Pij Pij is supposed to be sigma ij, but you are actually working on the source variable. So, the identity required is Pij of any xj is equal to sigma ij of qaj. Oh, right, exactly. Of xj. Oh, exactly, right, good. That would have taken me more time. Yeah. Okay. And so, and since this is a linear map, there is a linearized polynomial Pij which has exactly this property. Okay. So,
you want to say something about the degrees of the HIs?
An hi is just a linearized polynomial, because QAI is linearized and these are linearized, and the point is, right. So, the degree of hi in the variable xi is less than 2 to the is equal to, in fact, 2 to the m minus dimension of ai. And this is the crucial part, and hi has arbitrarily high degree in the earlier variables, and hi depends on no future variables. So, hi does not depend on xj for any j greater than I. Okay. Okay, good. So now we are ready to look at f composed with h and expand. Okay. And so this is it looks daunting, but it's not that daunting. So, f composed with h, and you want to show its so right, of x1 up to xs. Okay, well, what is it? Well, it's precisely trace of good sum over all i's contained in S, size of I equal to T, product over all i's in I of hi of x1 to xs to the power something, right. So, and the something was 2 to the I plus 1 minus 1. Okay. And so, I will call that alpha may be bad because I am going to use it, gamma I. Okay. And okay, so the most so the first trick actually that just seems, so so let me just write it here, gamma I. You would have, so I originally said that gamma I is going to be 2 to the I plus 1 minus 1, but actually I will flip the order of exponent. So, I will start with the highest degree thing first and the lowest degree thing last. This does not change the polynomial, it is just renaming the variables, but so to be s plus 2 minus I minus 1. Okay. So, this is just for technical reasons. Okay. So, good. So, it is this brackets are fine. Yeah, good. So, it is this thing that I want to show is non-constant when you substitute x1 up to xs sitting inside f2 to the m to the s. Okay, I want to show that this composed polynomial is non-constant. So, equivalently, if I look at this composed polynomial and look at its polynomial representation when you write it as in the unique fashion with degrees bounded by the field size minus 1. And if I can show that the unique polynomial representation of it has a non-zero monomial, a non-constant monomial with positive degree, right, with non-zero degree. If it has a monomial with non-zero degree which has a non-zero coefficient, then this is a non-constant polynomial, just because it has, when you write it as a polynomial, it's no, it's not, it has some things which are not constant in it. So, the precise thing that we want to study is to take this and reduce it mod xi to the 2 to the m minus xi as I goes from 1 to s.
This is all inside the trace.
Oh, this is outside the trace.
It's outside.
It's outside the trace. So,
So the trace doesn't matter to you, just wanted.
oh, so trace will matter because it will sum things up. I mean, so more precisely, this should have been sum over w going from 0 to m minus 1, this to the 2 to the m minus 1, 2 to the w. Okay, and this is one mega polynomial, and whatever it is, expand it out, reduce it mod this, and show that some monomial survived. Okay, not every monomial got cancelled. Okay, this is what the plan is, but it's not going to. So there are going to be some two simple reduction steps that will just bring us to the sub theorem situation. So it will be much simpler than it looks at the moment, at least. Okay, and so right. So you're expanding it all out, and so there's one nagging thing that I haven't mentioned anywhere is so somewhere in all this you're going to have to use the fact that m is prime, or that there are no subfields, because if there were any subfields, whatever polynomial you're plugging things in, all the arithmetic which you do, addition, multiplication, will keep you within the subfield, and then when you take trace of it, I mean you're not going to get it non-zero. So yeah, good. So there's a lot of faith one needs to have at this moment to start expanding, and so we'll try to do that now.
So I guess the faith came from the fact that you could do this before and for much louder. I mean, so well, S was a constant.
When
I mean, your faith in the ability to expand this came from the fact that before and you expanded it for very small s.
Right, when s was equal to 1, we were able to expand it and do some things which are slightly non-trivial, and here otherwise, right, I don't, it's not recommended as a strategy yeah, to expand everything you see. Right, okay. So let's expand it. Okay, so we'll need a big board now. Sub theorem, well, okay, I'll erase that one. And so one of the punchlines that I'm saving for near the end is here this assumption that AI is not contained in any small is not contained in affine shift of any subfield. So it's a very hard condition to use. It's not clear. So one way of using that AI is not contained in any subfield is the sum product theorem, which says that if AI is not contained in any affine shift of a subfield, then addition and multiplication of the set makes it grow. But so at least in this polynomial approach, it's not at all clear how to use the absence of subfields, or the fact that AI has nothing to do with the subfield. How does it show up in all this polynomial mess? And so that will be towards the end, and it's a really short, and it comes from nowhere to be So I really don't know why it comes. Okay, so good. So let's just look at hi, and so I had this complicated expression. Okay, so there's a 3-step plan. So first we'll find an we'll find an I0 inside S such that size of I0 is equal to T, and the sum of the dimensions of I in I0 is big. Big. Say. Okay, so we'll first find a collection of xi's of size t which have a lot of entropy in them. Okay, this is I mean the entropy in xi condition on the previous stuff is precisely the dimension of ai. So we'll first find a collection of xi's which have a lot of entropy in them. Then we'll we somehow want to go to this theorem and say that this theorem. Then we'll somehow want to go to this theorem and say that the function, just the monomial which corresponds to that I0. So for every I0 of size t, there is a monomial sitting inside that expression. The monomial corresponding to that I0 gives you some non-constantness, and then show that this is not spoiled by the remaining I0s. Okay, so more precisely, let me now state the modified version of the sub-theorem that is the one we will precisely use. Yeah.
Just a comment. So, where do you use the fact that this is not an extractor?
Where? Oh, because I'm just at the end of all this, I'm going to show that this thing is a non-constant polynomial, but its degree could be ridiculously high. And so
it's a linear polynomial because you're taking the linear polynomial mod linear polynomial.
No, so this is linear, but here in the product I'm actually these powers, and not only that, I'm also multiplying them. So it's already pretty non-linear, and it's very high degree, and so it has. So once we're done with all these once we're done with plugging it in, it has no structure, almost no structure left.
Cannot remain linear. There's no linear function which will be
Oh, right. And okay, so now we can state the modified subtheorem, which is actually what. So the modified subtheorem says that not only is this a non-constant, but it will tell you that the following monomial in some expansion is non-constant, has a non-zero coefficient. Okay, so here I'll state the strengthened subtheorem. So more precisely, trace of, so here I was looking at trace of product yi to the alpha I, where yi is varied over the subspaces ai. So another way of talking about the same thing is to look at qai of xi to the alpha I mod xi to the 2 to the m minus xi.
the product is over the whole field.
Right, exactly. So this is, if I call this h of x1 up to, not h, gh, r of x1 etc. to xt, then the claim is r is non-constant when you plug in the xi's over the whole field f2 to the m, which equivalently is looking at it mod xi to the 2 to the m minus xi, and showing that this thing is a non-zero polynomial. Okay, so more precisely, so if you look at this polynomial, then there exists b1 etc. up to bt such that if you set beta I to be sum over j in bi of 2 to the j, the coefficient of product xi to the beta I is non-zero, and also the size of bi is equal to ei plus 1. Okay, so let me parse this somewhat. So I want to say that there is a monomial which has a non-zero coefficient, and that monomial has a special form. So it's xi gets raised to the power beta I, and each beta I is a sum of exactly ei plus 1 powers of 2. Okay, so first maybe I should tell you, so what is the significance of raising x1 to the beta 1 where the where beta 1 is a sum of 10 powers of 2. I want to say that this is so this is exactly the same thing as this being a degree 10 polynomial over f2. Okay, so the subclaim here is, just to sort of shed light on this, is x1 to the x to the beta is a degree Hamming weight of beta in base 2 polynomial over f2. So, if you look at the map which maps f2 to the m to f2 to the m, that sends x to the beta, then this is actually a polynomial of degree. So, look at it as a function over f2. Over f2, this is an m tuple of functions, because it is mapping to f2 to the m. This is an m tuple of functions. Each of these functions has degree at most Hamming weight of beta when you write it in base 2, and one of them in fact has degree Hamming weight of beta. So, right. So this is what it says. It says that there is a certain monomial in this expansion which has a non-zero coefficient, where the coefficient is of a certain kind. Okay. And the fact that this coefficient is of a certain kind is going to say that, oh, when I look at that expansion, no other, I mean, you will get this non-zero coefficient from a certain term, and none of the other terms will have that same monomial with a non-zero coefficient. So, it can cancel out the non-zeroness of this coefficient. Okay. So let me let me now say this. Okay, good. So, where were we? Right, we were here. So, okay, so now since we are in this situation, we can now apply the subtheorem. Okay, so we have an I naught where the sum of dimension of AI is even minus, so it's greater than m and it's well greater than m. So, well greater than m is so that even the summation of di minus ei plus 1 is also greater than m. Okay, so this implies that the coefficient, so there exists beta 1 up to beta better. So, if I naught is equal to I1 up to IT, then there exists beta I1 up to beta IT such that the coefficient of product xi to the beta I is non-zero in trace of product over I and I naught QAI of xi to the alpha.
This you will prove assuming the subtheorem.
So, this follows from the subtheorem. Okay. Okay. So the problem is this isn't quite. So, I mean, this particular product, trace of product QAI of xi to the alpha, never appears in this expression. So, hi is not QAI of xi. Hi is QAI of xi plus some other stuff. Okay. So, but okay. So, now there are two simple observations that say that the coefficient of product xi to the beta I in this polynomial and in this polynomial, when you look at the term corresponding to I naught, are exactly the same.
For this particular I naught, which you have to say what?
Right, for this particular I naught. No. Huh? And in fact, for every I naught, it all it requires is that the size of the beta I is exactly it's of the beta i's are of highest Hamming weight possible. Okay, so in terms of f2 degree, the f2 degree of this is as high as possible given the function. So, I mean this is a t function that takes t variables and it is of degree ei plus 1 in variable I, and it shows that in the expansion of that polynomial there is a monomial of individual degrees ei plus 1 which has non-zero coefficient. So, more precisely, I mean this statement just says that when you look at the restriction of G to the subspace product A I, it is a full degree. It is the maximum degree that one could hope for.
So it is one of the maximum degree monomials survive.
One of the maximum degree monomials survive. Okay.
That's what you assume, and you say that if there is such, it will not get cancelled with the other.
With the other stuff. Okay, so because right, and in fact the maximum degrees monomials always survive. Okay, and a separate claim is that maximum degree monomials of any given I naught do not mix with maximal degree monomials of any other J naught. So, each I naught, the maximal degree monomials of that could not have come from any other set I prime. Okay, so okay, good. So the 3-step plan didn't quite work, but okay. So the second step is just to say it in words is that so I mean if I rewrite this as summation term sub I naught, then this implies that the coefficient of product xi to the beta I in term sub I naught is non-zero. This step 1 implies that the coefficient of xi to the beta I in terms of I naught is non-zero, and step 3 is that this implies that the coefficient of xi product xi to the beta I in the full polynomial, so summation term sub I over all sets I is non-zero.
But this would come from the fact that this monomial would not be generalized. So you're not proving non-cancellation. You're just going to prove that this doesn't appear in the other term.
This does not even appear in the other thing.
So it's not. It's a stronger claim, and that's probably the only way.
That's the only way one could have hoped to show it. Right. So this monomial, any monomial which is of maximal degree in I naught does not appear in any of the other terms. Right, and showing right when you're dealing with two non-zero things, showing that their sum is non-zero is hopeless. But if you're showing non-zero plus 0, that's always non-zero. That's a much. Okay, so well, good. So step 2 and 3, I didn't really get into the details, but okay, good. So all the action is now in the sub theorem.
But just you are not going to get into the details. But the point is the choice of coefficients, right?
Right, and all the action happened right in the choice of the coefficients. If you choose the coefficients slightly differently, then this uniqueness of monomials, etc., do not hold anymore. Okay, so right, so even in Bourgain's construction of extractors and even Meer's, I mean, it's again a long polynomial with very carefully chosen exponents, and these exponents always have to be carefully chosen in order for things like this to work. Okay, so right, so all we have to show now is the sub theorem. Okay, good. So and we have 35 minutes, which is very good. Right. So in fact, you even I mean, so given the sub theorem, you sort of believe this. So 4/5 is just an optimization of all the parameters involved. So so it was clear that it will give n to the 1 minus epsilon for some epsilon, but so if you so I can so I was thinking of telling you the parameters actual choice, but it's not very illuminating. So yeah, it's just optimization of something. Okay, so now the subtheorem. Okay, so we have T affine subspaces sitting inside F2 to the m. I am looking at the product of QAI of xi to the alpha I and the trace of this mod xi to the 2 to the m minus xi. Okay, and I want to expand this out and find a monomial with a non-zero coefficient. Okay, and the thing that's still nagging is we have not yet used anything about this. Right. So let me.
This reduction has to guarantee this property, or just the fact that m is prime guarantees this.
Is the right that m is prime already guarantees these properties, right? So okay, so let me start. I'll start by expanding things out, and at some point I'll get stuck, and then we'll find out where what is the correct incarnation of AI not being a subset of Bi times F2 to the I plus C. Okay, so suppose QAI of x is equal to some, or let's start with just a general. A is bad. Okay, QAI of x is summation AI x to the 2 to the I to n minus the dimension of AI, which I'll call di. Now then this should be Aij x to the 2 to the j. Okay, so the first step is just a very simple expansion. Yeah. So product of QAI of xi to the alpha I, trace of this. So and then reduce it mod xi to the 2 to the m minus xi for all I. Okay, so I'll first so the trace is just again sum over all w going from 0 to m minus 1, this to the 2 to the m minus 1. So to the w min. Okay, so this I can bring here, and now I can just expand it out. Okay, so at this point I just so what is not so daunting about the expansion is that so alpha is actually 1 plus 2 plus dot 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 up to 2 to the ei. Okay, I'll leave the w. Okay, and so QAI of xi is QAI of xi to the, I mean, so this to the power 1 plus 2 plus up to 2 to the ei is the product of so it's this sum times this product of QAI of xi to the 1 times QAI of xi to the 2 dot 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 QAI of xi to the 2 to the ei, and this is 2 to the w. Okay, and QAI of xi to the 2, well, squaring is a linear operation over F2, so the 2 can come into the expansion. So okay, so at this point it's at a stage where one can just sit and try to write out the expansion in terms of the coefficients of the subspace polynomial, and so now I'll just claim what the final expansion is, and it's once I tell you what it is, it's very easy to check, and it's not illuminating how it works. So so this is so in fact if you let me I'll assume all the ei's are equal to 1 and all the di's are equal to the same thing d. So I guess that's a pretty, I mean, so all the action, I mean, the same kind of stuff happens there. So all the ei's are equal to 1 and all the di's are equal to d.
The values of the EI were used before to make sure there are no interference between the different terms.
Exactly.
Here it doesn't matter.
Here it doesn't matter, right?
Just need the gap.
Right. And okay, so I'll define M1 to be the following matrix A0 So, so this is referring to the first polynomial. So, the first polynomial has coefficients A10, A11 up to A1 n minus d 0 0 up to 0. So, I am referring to coefficient, right. So, I am taking all the powers of 2. So, this is the coefficient of 2 x to the 2 to the 0, this is the coefficient of x to the 2 to the 1, etc. This is the coefficient of x to the 2 to the m minus 1, and we know that this happens to be 0. Because q a I is a polynomial of degree only n minus d. So, already at 2 to the n minus m minus d, already at 2 to the m minus d we saw the last non-zero coefficient, after that it is all zeros. Okay, and in this, so and it is a 2 row matrix. The second row is you take the previous row, you square it and you cyclically shift it. Okay. A10 square, here is a 0, A11 square, then A1 m minus d square, that is built in 2 to the m minus d plus 1, and then 0 0 0. So, that is the matrix M1. Similarly, M2 you do the same thing with the coefficients of QA2. Here I took the coefficients of QA1, here I take the coefficients of QA2, etc. Okay, and all the way down to MT. Okay, so, now the claim is the coefficient of, okay, so all the EIs were 1. So, I need to produce beta i's with Hamming weight 2, right. So, that was the statement of the theorem, right. So, there exist sets B1 up to Bt such that beta I is the sum of powers of 2 where each Bi has exactly size 2. So, beta I is 2 to the good. So, the coefficient of x to the 2 to the B1, x2 to the 2 to the B2, xt to the 2 to the Bt. So, here I am writing 2 to the B1 to be 2 to the, so the notation is 2 to the B is summation 2 to the little b b in capital B. Okay. So, the coefficient of x to the 2 to the B1, x to the 2 to the 2 to the B2, etc. will xt to the 2 to the Bt in that expansion is equal to the sum over all w going from 0 to m minus 1, product I going from is it I? Yeah, 1 to t of the following thing, the permanent of m I. So, take m I, look, so take m 1, look at the columns corresponding to B 1 shifted by w to the 2 to the w. Okay. So, so m I of a set B, by that I mean if B is of size 2, then that gives you the sub matrix of m I when you restrict to those two columns. Okay. So, the coefficient of x 1 to the 2 to the B 1, x 2 to the 2 to the B 2, etc., x t to the 2 to the B t is, well, look at, well, it is a sum of m terms. The first term is, well, I select B 1 here, I select, so B 1 each B I has 2 elements which indexes 2 columns inside this. I select B 2 here, I select B 3 here, I take the permanent of this 2 by 2 matrix, this 2 by 2 matrix, this 2 by, I take the permanents of all these matrices and multiply them. Okay. That is the first term when w was equal to 0. That is the sum of the products of the permanents of m I of B I. The second term is, oh, now I take all these B I's and shift them back by 1, these B I's shift them back by 1, do the same product of the permanents and now raise it to power 2. Okay, so this should look sort of messy, but right, but then what I want to do with it is going to be very simple. Okay, so if I want to show that some monomial has a non-zero coefficient, then it suffices for me to do the following. So want the following. So we want B1 up to Bt each of size 2 such that good. So I want to make the W equal to 0 term of this non-zero and the W non-zero terms of this 0, so that when you take the sum you get a non-zero coefficient. So for all I permanent of Mi of Bi is non-zero. So this is the first thing I want. The second thing is for all W non-zero. So I mean in 1 to 3 up to 2 to up to m minus 1, the permanent there is some I such that the permanent of Mi of Bi minus W is 0. Okay.
Some pigeonhole that will come from the sum of dimensions. From the fact that these large relative.
This is a pigeonhole that will come from the sum of.
Well, you have many zeros floating.
Right. So there's going to be a pigeonhole that comes from this. Exactly. Yeah. So I want an I such that so I want to choose sets B1 up to Bt such that, well, when you look at the W equal to 0 term of this, all the terms in this product are non-zero. Therefore, this term turns out to be non-zero. But for any other shift W, one of these permanents ends up being 0. Okay, that will ensure that the sum of all these terms is non-zero.
In fact, the VIs are forced on you because the only information you have about non-zeros of the coefficients is about the highest coefficient.
Right. So, but okay, but there's going to be a small catch. So the thing that we haven't yet used this absence of subfields, and this is going to show up somewhere. But right, so there's a very natural choice of BIs that I will make, and it will almost work, assuming all the coefficients aij's are non-zero. Okay, so if all the coefficients of the image subspace polynomial of the sets ai happen to be non-zero, then there's a very simple choice that will actually implement this full plan. But with the coefficients of the image subspace polynomial of a subspace are some ridiculous creatures. I mean, the proof that it even exists, I mean, you can't even get your hands on it. So and that is where the absence of subfields will come in. So just by some completely different trick, the absence of subfields will mean that the coefficients of the image subspace polynomial are very often non-zero. Okay, and this will finish it off. Okay, so in the this is fine, right? So in the non-zero setting, let me give you a simple geometric choice of the BIs. So assuming all aij's are non-zero. Okay, let's do something. So we had our matrices. This was M1, M2, and this is MT, and I have A0 up to A m minus okay, so let me go more, A m minus D, A0 up to A m minus this is A10 up to A1m minus d, A20 up to A2m minus d, and okay. So the non-zero elements, they sit inside this parallelogram, just to, and the potentially, right. So all these elements are non-zero by our assumption. Similarly here, right, all these elements are non-zero, and then there's a sort of big sea of zeros over here. Okay. So how can I ensure that so I'm not going to use anything deep about the permanent. The two things I'm going to use is that, if you take a permanent of an upper triangular matrix, then it's non-zero, which an upper triangular matrix which has non-zero elements on the diagonal, then it's non-zero. If you take a permanent of a matrix which has a single 0 column, then it's 0. Okay, so these are the only two properties of the permanent that I'm using. Okay, good. So let me show you what B1 is. Okay. Okay. So first, I'll pick. So the assumption is still there. So first, I'll pick evenly spaced points. Okay, from 0 up to. So this is 0. This is d minus 1. This is 2 times d minus 1. This is the point something, probably m minus d. Okay, so I pick evenly spaced points from 0 up to m minus 1 with spacing d roughly. Okay, and okay, B1 is going to be the set this and this. Okay, B2. So let me select it here. This, or maybe a different color. This and this. B2 is going to be the last column and the second guy here. B3 is going to be the last column and the third guy here.
The last is aligned, right? I mean, they're all in.
So the last column consists of 0 and a m minus d. Okay, and so I keep doing this, and the very last column, well, since the number of subspaces is so, I mean, I had an assumption, right, that the sum of the dimensions is greater than m. So in particular, d times t is greater than m. So by the time I have reached the last subspace, I mean, I would have selected two guys which are, nearly here. Okay, so I want to say that at this point, this setting of BIs actually just works. Okay, why? Well, let's first consider the 0 shift. Okay, so the mi of bi, m1 of b1 just looks like, well, there's a 0 entry here, there's some non-zero element a sub m minus d square here, and then there are two non-zero elements here, right, because of our assumption that all the elements in all the coefficients of these subspace polynomials were non-zero. B2 looks exactly the same. There's a 0 entry here. There's a non.
First one at the bottom also 0 because you picked the first column.
Oh, right. So here the very first column happened to have a 0 there too. Okay, and then I have some two non-zero elements here. This is for B2, etc. The very last BT also has exactly the same set of 0, some non-zero element, and some two non-zero elements here. Okay, so it's all the permanents of all these guys are non-zero. Okay, and this gives you property 1. Okay, so for property 2, well, okay, so now I want to say, so look, the sea of zeros out here is of size d. Here I have a whole bunch of BIs which are spaced d minus 1 apart. So now if you take any shift of them, I mean, so the only gap between the BIs is this big C of size d. So it's just a sort of intuitive picture. So I have a circle, I mean, I have evenly spaced points at with gaps d minus 1 and at the end I have a sea of zeros of size d. Now, any rotation other than the, if you are doing any rotation which is non-trivial, one of these columns is going to end up in the sea of zeros, and so the permanent is going to be 0. Okay, so right, and so that's it. So this gave you so this gave you the second thing. Okay, so what was the catch? The catch was the assumption that all the coefficients of the subspace polynomial are non-zero. Yeah.
Can you try somehow to use? I don't see how you use this property.
Yeah.
But can you use the fact that n is prime to argue something? Did you try to do this?
Oh, that's a very.
There is an arithmetic, like everything has an inverse. This is p elements, and you need some.
Oh, so that's a good one. So the question is, could it just follow from the primeness of M that whenever you that there is always some subset of columns such that when you do rotations it works? So that's a very good question. We tried a lot.
You don't know anything about that. You don't want to use anything about the coefficients of the subspace.
Just
Each matrix has like a list of integers from 1 to n, from 0 to n.
No, but the matrices contain coefficients of the subspace polynomial.
Yes,
So
at
you
least one
don't
of
want to
them is
assume
non-zero.
one of them, yeah.
Yes,
That's why.
one of them meaning?
it's non-zero.
Oh, right, one of them is non-zero, right? That's a good one. So if there are more zeros in a way, if there are lots of zeros in the coefficients, then in a way it helps you, because then it's easier for a permanent to become 0. Okay, so where did I use the assumption that all the coefficients are non-zero? In the statement that no, the starting of permanents were non-zero. So maybe there's some other thing you can do, which so I don't know at all, but there's some very good questions here that I mean if true should be just basic questions about rotations. Okay. Okay, so now I'll just wrap up with the lemma about the coefficients of subspace polynomials that follows from this. It says that you cannot have too many zeros in the coefficients of subspace polynomials in a certain way. Okay, and once you have that, and an idea very similar to this, we'll just finish the proof, but I won't do that. So okay, so this is a completely new sorry, not new. This is a completely, it has nothing to do with everything we've done so far, so we can just start afresh if we're asleep. Okay, so no, so and the thing to remember is that it's false if there are subfields. So it has to be a delicate property that comes in. Okay, so here is the theorem. So let
Maybe you should use white.
oh, I had a good one recently.
The box is red.
Okay. So A contained in f2 to the m is a subspace. QA is the image subspace polynomial of A, and A is not contained in B times f2 to the r plus c for all b, c and r less than. So this in f2 to the m, that is, and r less than m.
Maybe not m, the dimension of m.
Yeah, m, I guess. Okay, then so let's write QA of x as summation ai x to the 2 to the I going from 0 to m minus 1. Okay, then for any, so the claim is that for any interval of size oh wait, so did I give a dimension? Yeah, so and dimension of A is equal to D. Then for all right, so then look at these coefficients. Okay, so I write A0, A1, A m minus 1, but actually okay, so m minus d. Yeah, so look at the coefficients of this. Then there is no interval of length d minus 2 that is non-zero. Pardon? Where all of them are 0. You cannot have an interval of very long length where all the elements are 0. So I'll write it there. For all intervals j to j plus d minus 2, there exists a j. So yeah, where it's clear. So the j is only live between these. Okay. Okay, so the fact about f2 to the r, I am not going to say it until I use it, and then we can discuss it. Okay, good. So let's see. So qa of x, okay, is summation ai x to the 2 to the I. Okay. Now I want to look at qa of x to the power 2 to the j for some j. Power 2 to the j, well, this is simply summation ai to the 2 to the j to mx to the 2 to the I plus 2 to the j. Okay. And if I look at this polynomial mod x to the 2 to the m minus x, okay, then all it does is it takes, oh sorry, that is 2 to the I times 2 to the j. So, that is 2 to the I plus j. So, yeah, I will even write it that way. Then if I look at this polynomial mod x to the 2 to the m minus x, all it does is it takes I plus j and reduces it mod m. Okay. So, now if I, okay, so let me see what this operation does to the coefficients if I write them out like this. So, this is coordinate number 0, this is coordinate number m minus d, and I have written in each of these entries the coefficient ai. So, here is a0 and here is a m minus d, and then followed by zeros up to coordinate m minus 1. Then when I raised it to the power 2 to the j, what happened was that the elements got raised to the power 2 to the j and then got rotated by j. Okay, so they got shifted by j and things wrapped around to the beginning. Okay. Okay, so now suppose there was a sea of zeros in here which are all zeros. Okay. Then okay, so I want to find a rotation of this that will bring this sea of zeros and bring them in front here. Okay, and there is always such a rotation. So, if the size of the sea of zeros, so this is a sea of zeros of length d minus 1. If the size of this sea of zeros is also of length d minus 1, then I can bring one and align it up. Okay, so suppose not, then there exists a j such that qa of x to the 2 to the j mod x to the 2 to the m minus x right has degree strictly less than or less than or equal to m minus d, right, that is what I meant, 2 to the m minus d, sorry, right. Okay, so first let me rule out the fact, let me rule out the degree being strictly less than 2 to the m minus d. Right, exactly. So, qa of x is a polynomial that vanishes on, so it is an image subspace polynomial of A, but it is also the kernel subspace polynomial of some other set, and it vanishes on the same number of points as its degree. So, if you now raised it to the power 2 to the j and reduced it mod this, then the values that it takes are still the same, and it's so it's still 0 on the same set. And so it's, if its degree turned out to be less than 2 to the m minus d, then that's it. I mean, then we have a contradiction. We have a degree polynomial of degree strictly less than the number of roots. Okay, so good. So I mean, so and here we didn't even use the absence of subfields or anything. So let's assume that there is a j such that q of x to the 2 to the j mod this has degree exactly 2 to the m minus d. Okay. Exactly. So it has to be essentially the same polynomial. Yeah. So I'll keep this. Right, and so that's exactly the proof. So that means there is some c such that qa of x to the 2 to the j minus c times qa of x. Well, qa of x to the mod x to the 2 to the m minus x. Then this thing is a polynomial of degree strictly less than 2 to the m minus d. So but note that this polynomial also vanishes on the same set where a vanished, because well, this polynomial vanishes and this polynomial vanishes. So this whole thing vanishes also on the same set of size 2 to the m minus d. That forces that this polynomial must be identically 0. Okay. So now we are almost done. So what do we have? qa of x to the 2 to the j minus c times qa of x mod to x to the 2 to the m minus x is identically 0. Okay. So well, since this is identically 0 mod x to the 2 to the m minus x, if you plug in any substitution of x from the field f2 to the m, then this still vanishes. Okay. So what we know is for all little x in f2 to the m, qa of x to the 2 to the j minus c times qa of x is equal to 0. So this means that for all, so qa of x just is some element of a. So for all, and every element of a is representable that way. So for all a in a to the 2 to the j minus c times a is 0. Okay. So this I want to say we're done. So if c was 1, now we're really done, because then what you get is a to the 2 to the j minus a is 0, and this is precisely the equation defining the subfield f2 to the j. And so then the thing to check is that if a to the 2 to the j minus c times a is 0, then this means that a is inside. Okay, so I don't remember this, it's c to the some power times f2 to the j. And that's it. So this is where the absence of subfields came. So we just conclude that for every a in a is inside some subfield, some constant multiple of a subfield of the appropriate size. Okay, so one actually has to be a little delicate and make sure that f2 to the j is actually a subfield of f2 to the m. It could be that, I mean, the power of c which you take could take it out into the algebraic closure somewhere else, but okay, so that doesn't happen. But so that's it. So I actually said is not contained b times f2 to the r plus c. So the plus c comes, so everywhere I should have paid attention to the constant term in the affine subspace polynomial, but I didn't. So, but had I, then I would have gotten the correct theorem. Okay, and so that's basically it. So having got the non-zeroness of, I mean, you cannot have too many zeros in the coefficients of a subspace polynomial in intervals, then this plugs into this kind of proof in a pretty modular way, and that finishes it off.
Questions? So where do you think that, well, first of all, what is the degree of the polynomial in terms of n?
The degree of this as an f2
to the n to the epsilon or something like this, the degree of the polynomial you produce.
Right, it's 2 to the n to the 3/5 or something, right?
Yeah, something like this. So you could hope that maybe you can do an exponential sum on it, right? I mean, if that's the degree. You prove that it's non-zero.
Sorry. You mean
if you want an extractor rather than a disperser, there are two things you need to do, right? First, show even for this polynomial that there is cancellation. That's a trace.
Oh, I see. No. So then I take that back. So sorry, as an F2 polynomial, it has degree n to the 3/5 as an F2 polynomial on n variables. But as an F2 to the m polynomial, it has degree nearly 2 to the m. So 2 to the m minus 10 or 2 to the m minus 1. It has, because once you take trace, it's a extremely high degree polynomial. Or are you talking about before taking the trace?
Before taking the trace.
Oh, okay.
So so what is the answer? What's the degree of the polynomial?
Oh, so sorry, sir. So before taking the trace, also once you plug in the subspace polynomials, the subspace polynomials are already very, very high degree. So the
All the monomials you prove exist are the highest degree possible.
the highest F2 degree possible.
Fine. So let's consider only the F2 degree. What's the F2 degree?
This
Small power of n.
small power of n. Yeah.
Small power of n. So the trace of this should, when you run over the whole field, which you do, right? Because you already incorporated that. It's a complete character sum.
Right.
So this should just by veil or something should have cancellation.
Right. So this is the monomial we show has a non-zero coefficient, but there are other.
That's why I asked. It's not the highest degree.
No, it's not the highest F2 to the m degree one. It's only the highest F2 degree one.
Yeah, but then you can do the character sum in F2. But you need to do it for, it's not just the initial polynomial, but I mean, you can, when you do this exponential sum, you have to do it over all characters, but all characters will be just instead of trace of the polynomial, will be the trace of the polynomial times any
Constant.
Any element, any constant from the field to the m, right?
Right.
So if you could do the existence, I mean, if this wouldn't kill your polynomial, and furthermore, when you move to F2, it will be a low degree, then maybe you can just use veil.
No, so I think I'm pretty sure it's high degree once you. So the degree is higher than what veil allows.
This veil you need the degree to be square root of the field size, like 2 to the m minus 1.
Yeah.
Right. So if it's like
2 to the m over 2.
No, the field size is 2 to the m.
2 to the m.
So 2 to the m over 2 is the.
The square root of it.
Yeah, right, and that's far.
Yeah,
We beat that completely. Yeah. Right, so extractor I don't see. Right, so the subspace polynomial type things I may not have anything to say about extractor at least so far.